Okay, welcome back. So from the break, this is part two of the lecture. So um, finishing off the discussion of the chi-square distribution. So as I mentioned, it's closely related to the gamma distribution, and then the other key point, and what we're going to see later, and as I mentioned, the reason why this distribution is useful, just like the others, is that it's going to be very closely related. Like we're going to see that, in fact, other statistics have this distribution both asymptotically and exactly. So if we have Sn squared, which is the sample variance, here where we assume that these are normal. So this is if we have standard normal random variables, we're actually going to see that this statistic actually has a chi-squared n-1 distribution. We're going to cover that in more detail in lectures to follow. This is just to give you an idea of why this is actually relevant. So the next thing is the t-distribution. So you have a number of you have potentially heard of the t-test. Or the t-statistic, and so this is where the t-distribution essentially comes from. So this is related to the t-test or t-statistic. So what we're going to do is we're going to define T of n in terms of, once again, I mentioned that all of these distributions can be constructed as functions of standard normal. So here, remember here, so what we're saying is that z here is a standard normal. And then chi-squared n distribution, and that z and chi-squared of n are independent. Okay, then we say that T of n is a t distribution with n degrees of freedom. So once again, we have here that n is the degrees of freedom. Okay. Again, so this is this is basically how the t distribution gets constructed. Sorry. And now we'll look at some of these properties. So So what's the range here? We've got a standard normal here, which has the general support of negative infinity to infinity, and we're dividing it by a non-negative number. So the range is going to be negative to infinity, and then we know that so. I'm not going to go through this this calculation, but I'll give a little bit of description of it shortly. We have the expectation of T of n is 0, and the variance of T of n is actually n over n minus 2. So it's It's valid. For n bigger than 3, bigger than or equal to 3. So it's what it is it's like a normal distribution with heavier tails, basically. So and hopefully the intuition behind this will become clearer. So so you can think of this as normal with heavy tails when n is small. For n large, it's basically just like a normal, so it's just going to just look like your kind of standard normal here. And again, my drawing here is my drawing ability here is a little bit limited, but essentially it looks like a normal. And there's a couple of different ways to see that. So if we note that the variance of t of n is n over n minus 2, and then we know that the variance of a standard normal z here is just 1. So we can see that as n gets large, variance of t of n close to variance of z. The variance of t of n may be so for small n, the variance of t of n may be quite a bit larger than that value of 1. And so and what you'll see is what small and large mean is obviously, like, different depending on what you're looking at. But even if you go as large as n as, say 30 to 50, you'll see that there's very little difference actually between the t distribution and the normal distribution. So that's like the t distributions used and the t-test is used as a way to get a slightly more accurate test. We'll see for some for some cases, but it's most of the time the results are going to be quite similar if you use the z-test or the normal distribution. So and then the reason that it is relevant, and we're going to see this very shortly, is that if we we're going to define this t statistic with subscript n here is just if we have that these are normal with a mean of 0 and a variance of sigma squared. So now the variance is actually unknown. So we look at x bar n over Sn. Or actually, let me just state that that's... this is just standard normal here. It's standard normal. Then T of n as a t distribution with n minus 1 degrees of freedom. So this is another statistic that we're going to see. So okay, and we're going to see this, see how this is useful later. Recall that Sn here was the sample standard deviation, or the square root of the sample variance. Okay, and the and just I'll mention here that the key thing here is not necessarily to know the PDFs or the forms of these distributions, just how to use them. Because what we're eventually going to use is to just use the tables, just like we use a z table. You can use a t table or a chi-squared table, or we'll see later the f table. So the final distribution that we're going to see today is the f distribution. And this is a test we're going to see a couple of times. It's related to the f test. And once again, it's constructed out of standard normals, or in particular, we'll see that it's chi-squares. And here we're actually going to have two parameters, or degrees of freedom. So we're going to define this random variable f of m over n, which is and we're once again assuming that these chi-squared of m, chi-squared of n random variables are independent. Then what we have here is that is given by this f distribution, and the mathematical form of this PDF is quite complicated, so I'm not really going to talk too much about this about where that comes from, but just know that this is the f distribution. And then what we can see is that if you plug in what do we get if we plug in f of 1n? This gives you exactly the same distribution as the t distribution. So I should use this notation here. So if you look at f of 1 n, this is tn squared. So this is one like relationship that you can kind of think about to remember that. So we can just see that z squared obviously has a chi-squared of chi-squared 1 distribution. So if z is standard normal, then z squared's got a chi-squared 1 distribution. And once again, I've tried to distinguish between what's a random variable and what's a distribution by using brackets to indicate that it's a random variable and subscripts to indicate that it's a distribution. I know this might be a little bit confusing, but that's the notation that I'm using here. So chi-squared here and f and t both refer to random variables and distributions, where I'm distinguishing between subscripts for distributions, and brackets for random variables. So we can see that and so this is going to be a t squared n a t squared n distribution. So once again, you can see that you can see that the range here is once again 0 to infinity. And because we're dealing with we're dealing with the square of a random variable. So this is the main property that we can kind of deduce from this random variable. And again, we don't need to know a lot about this other than how to use it. We're going to have an F table when we need to use this. So just to summarize what we've learned in the distributions that we're going to see and we're going to use. So we have the chi-squared, which is the sum of these squares, the sum of these independent normal squares. So we're assuming that they're independent. We have that okay, so this is how we build up from the standard normals by basically squaring them and construct these three different sets of distributions. And all of those are going to be useful in all of these are going to be used and very useful throughout this course. Okay, so that'll be it for today's lecture. And so next week we're going to move on to finishing off chapter 6 and then moving on to chapter 7, where we get to start to use these distributions a little bit more to look at statistics and distributions of statistics of interest. Okay, thanks very much.